Hey guys, tonight we're going back 8,200 years to a single morning that rewrote the map of the world. Not slowly, not gradually, not over centuries of gentle erosion, but in the space of a few hours, on a day that began like any other day in the long human story of the land that lay between what we now call Britain and continental Europe. By the time that day ended, something had changed that would never be undone. A coastline that had stood for thousands of years was gone. A homeland that generations of people had known, had hunted across, had buried their dead in, had built their lives on, was beneath the sea. And the island we call Britain was, for the first time, truly an island. Before we begin, take a moment to subscribe, only if you genuinely enjoy what I do here, and drop a comment telling me where in the world you're listening from and what time it is for you. Now dim the lights, get comfortable, and let's ease into tonight's journey together. To understand what was lost, you first have to understand what existed. And what existed 8,200 years ago is so different from the world we know that it requires a genuine act of imagination to inhabit. Stand on what is now the eastern coast of England, on a cliff above the grey North Sea, and try to unsee the water. Try to replace it with land, because that is what was there. Land, stretching eastward for hundreds of miles, connecting the island that would become Britain to the continent that would become Europe, in a continuous, unbroken plain that geologists now call Doggerland. Doggerland was not a marginal landscape, not a barren edge of something more important. It was a heartland. At its peak, during the coldest part of the last ice age, when sea levels were much lower than today, covered an area roughly the size of modern France. Even by 8,000 years ago, after millennia of gradual sea level rise had already swallowed its western and southern edges, it was still substantial. A landscape of rivers and wetlands and gently rolling hills and reed beds that stretched across what is now the southern North Sea. Our three companions tonight are drawn from three very different relationships with this lost world. There is Calder, a Mesolithic hunter whose people have lived in this landscape for generations, not a specific named individual from the historical record, because the historical record of this world is written in flint and bone rather than words, but a composite of the human reality that the archaeology reveals. A person who knows every river bend and every seasonal hunting ground in a world that is about to be transformed beyond recognition. There is Dr. Ingrid, a marine geologist at a Norwegian university who has spent 20 years studying the underwater slopes off Norway's coast, and who has made it her life's work to understand the mechanics of what happened on that morning 8,200 years ago. And there is Rowan, a British archaeologist who works in the coastal peats and sediments of the North Sea shores, pulling fragments of the drowned world back into the light and trying to read in them the story of the people who lived and died there before the sea came. The landscape that Calder knows is one of extraordinary richness. The rivers of Doggerland drain eastward from the hills of what will become Britain, and westward from what will become the European mainland, meeting in a broad central plain where the Thames and the Rhine once flowed together into a single great river before that river reached the sea. This combined river system created a wetland environment of enormous productivity, a delta and estuary landscape of the kind that supports some of the densest concentrations of wildlife on Earth. waterfowl in numbers that would seem impossible today, fish runs of salmon and eel and sea trout moving through the river systems on a scale that has no modern equivalent, red deer and aurochs grazing the grasslands above the floodplain, wild boar in the oak woodlands on the higher ground, hazelnuts and wild strawberries and the roots of reed and rush providing plant food through the seasons. Calder's world is not a world of want. It is a world of managed abundance, a landscape that a community of skilled hunter-gatherers can read like a library, knowing where the geese come in autumn and where the salmon run in spring and where the hazelnuts will be thickest in late summer. The Mesolithic people of Doggerland are not struggling to survive in a hostile environment. They are thriving in a productive one, and the evidence, the middens of shells and bones, the carefully worked flint tools, the occasional wooden structure preserved in anaerobic sediment, speaks of communities that are successful by any measure. But the world is changing, and has been changing for a long time. Sea levels have been rising since the end of the last ice age, when the great ice sheets that covered much of northern Europe began their retreat. That retreat has been releasing water into the oceans for more than 10,000 years by the time our story reaches its crisis point, and the effect on Doggerland has been gradual but relentless. The western edge of the plain, closest to the Atlantic, has been swallowed first. Then, the southern edge, the land bridge between what is now southern England and what is now northern France, has narrowed from a broad plain to something more like a ridge, and the waters to the north and south of it have been creeping inward. Calder's people have lived with this slow change all their lives, and their parents lived with it, and their parents' parents. The sea takes a little more each generation. The old hunting grounds that the elders remember are underwater now. New ones have been learned. The community adapts, as it has always adapted, as the Mesolithic people of this world have been adapting for thousands of years. What Calder does not know, cannot know, is that this gradual process is about to be violently interrupted. The physical geography of Doggerland has been reconstructed by scientists with remarkable precision over the past 3 decades, primarily through the analysis of seismic survey data originally collected by oil and gas companies exploring the floor of the North Sea. That data, never intended to reveal the shape of an ancient landscape, turned out to contain exactly the information needed to map it. The echoes of sound waves bouncing off underground structures can be read to reconstruct the topography of landscapes that have been buried under sediment for thousands of years. What that data reveals is a landscape of considerable variety. In the north, where the water was deepest even before the final inundation, there were lower-lying areas that would have been wetland and shallow lake country, even during Doggerland's peak. In the centre, the great river system, the combined drainage of the Thames and Rhine and their tributaries, created a broad valley that ran roughly east-west across the plain. On either side of this central valley, higher ground rose to hills that would have been well-drained grassland and woodland, the kind of terrain that supports large grazing animals and the hunters who follow them. Rowan has spent years working with this seismic data, and she finds in it something that goes beyond geology. The rivers that she can trace in the underground topography are real rivers that real people once crossed and fished. The hills that show up as higher reflections in the data are hills that people once climbed to look for game, to orientate themselves, to find their way home. The bays and inlets of the coastline that existed before the final submersion are coastlines that people once walked, collecting shellfish and watching for fish. The data is geological. The reality it describes is human. The Dogger Bank, the shallow underwater ridge that gives the region its name, was one of the highest parts of Doggerland, a broad plateau of higher ground that may have remained above water as an island for some time after the lower-lying areas around it were flooded. It is from this ridge that trawler men pulling nets across the North Sea floor have for centuries occasionally brought up artifacts of the lost world, fragments of worked bone and antler, pieces of flint showing unmistakable human craftsmanship, even, on occasion, the bones of the animals that once lived on the plain. These chance recoveries, pulled up from the seafloor and examined in the lantern light of fishing boats by men who did not quite know what they were looking at, are the way in which Doggerland first made itself known to the modern world. The most famous of these chance recoveries happened in 1931, when a fishing trawler operating in the southern North Sea brought up a lump of peat in its nets. Tangled in the peat was a barbed antler harpoon point, an elegant, carefully made tool that was clearly the work of skilled hands and that dated, when it was eventually analysed, to the Mesolithic period. The fisherman who hauled it aboard had no idea what he was holding. He was holding the work of someone who had lived on dry land in a place that is now under 20 meters of water, who had made this tool with care and used it for a purpose, fishing or hunting or marking territory, and had lost it or discarded it in a world that no longer exists. Calder knows the Dogger Bank as high ground, reliable ground, ground that stays dry when the lower plains flood in a wet season. It is a place that people return to, a landmark in a landscape that changes with the seasons and the decades. The communities that use it know its contours the way a modern person knows the streets of their neighborhood, not by looking at a map, but by living in it, by moving through it, by carrying its geography in their bodies as a form of knowledge that does not need words to be real. Off the coast of Norway, in water that is now several hundred meters deep, there is a scar on the seafloor that is 290 kilometers long and 80 kilometers wide. It is called the Storegga Slide, and it is the physical evidence of one of the largest submarine landslides in recorded geological history, an event in which approximately 3,300 cubic kilometers of sediment broke loose from the continental shelf and slid down into the deep ocean, triggering a tsunami that would travel across the North Sea and change the world. To understand how a landslide on the seafloor causes a wave at the surface, you need to think about displacement. When 3,300 cubic kilometers of material suddenly moves, not slowly, not gradually, but rapidly in a matter of minutes, it displaces the water above it and around it with enormous force. The seafloor drops away in places and rises in others as the sediment flows downslope, and the water column above it reacts to these sudden changes in the terrain beneath it. The energy is transferred from the moving sediment into the water, and the water begins to move in ways that propagate outward from the source as waves. These are not the waves you see at the beach, driven by wind and shaped by the interaction of wind and water over hundreds of miles. These are waves driven by the displacement of the seafloor itself, waves that carry the energy of millions of tons of moving sediment, waves that travel not just at the surface, but through the full depth of the water column. In the deep ocean, they are barely visible, a rise and fall of the surface of perhaps a meter or less, moving at speeds of up to 800 kilometers per hour. They look like nothing. They are carrying everything. The conditions that made the Storegga slide possible had been building for a long time. The continental shelf off Norway is loaded with sediment, material that has been deposited over thousands of years by rivers, by glaciers, by the slow rain of organic material from the surface waters. During the last ice age, this sediment was locked in place, partly by the weight of ice above it. As the ice retreated, the sediment was no longer stabilized in the same way. Water percolated into it from above. Methane gas, produced by the decomposition of organic material in the sediment, built up in pockets within it. The slope became less stable with each passing year, loaded with material that was no longer as well supported as it had been during the glacial maximum. Dr. Ingrid has spent her career studying the sediment cores pulled from the Storegga region, and she has developed what she describes as a complicated relationship with the slope. It is the subject of her professional life. She knows its structure in the way that a physician knows the structure of the body, with the intimate knowledge that comes from years of looking at the same thing from different angles with different instruments. She knows where the failure planes were, where the water content in the sediment was highest before the slide, which layers were most vulnerable to liquefaction when the shaking began. She knows the anatomy of a catastrophe. What triggered the actual slide is still a matter of scientific discussion. The most widely accepted hypothesis is that a large earthquake, probably associated with the isostatic rebound of Scandinavia as it rose from the depression caused by the weight of the ice sheets, set off the slide by shaking the already unstable sediment beyond its yield point. The Earth had been rising steadily since the ice retreated, the same process that is still measurable today in parts of Scandinavia, where land continues to rise at rates of up to a centimetre per year as it recovers from the load it carried during the glacial maximum. A major earthquake associated with this process would have been felt across a wide area. In the sediment of the slope, already loaded and already at or near its threshold of stability, it would have been enough. When the slide began, it began fast. The failure propagated along the shelf in a matter of minutes, section after section of sediment losing its cohesion and beginning to move. The sound of it, if you could have heard it from the shore, would have been unlike anything in ordinary human experience. A deep bass vibration transmitted through the water and the rock, something felt in the chest before it was heard by the ears, the geological equivalent of a thunderclap. And then, in the waters above the sliding sediment, the wave was born. Calder is asleep when it begins. Or rather, the person whose experience we are imagining, the composite figure of a Mesolithic Doggerland inhabitant on that morning, is asleep, in a camp on the higher ground of the Dogger Bank, in a world that is about to become unrecognizable. The Storegga tsunami did not reach the coast of what is now Scotland and Britain as a single wave. This is one of the most important things to understand about large tsunamis, and one of the things that makes them so different from the waves of popular imagination. The wave that left the Norwegian shelf was not a single crest of water, moving through the ocean like a ripple across a pond. It was a train of waves, a sequence of crests and troughs, following one another at intervals of perhaps 20 minutes to half an hour, each one carrying a significant proportion of the total energy of the event. In the deep water of the Norwegian Sea, the waves are travelling at speeds that are difficult to comprehend in human terms. 700, 800 kilometers per hour, faster than a commercial aircraft. At this speed, the waves are barely perceptible at the surface. A ship in the path of the wave in deep water would have risen and fallen by a meter or two at most, and the rise and fall would have taken long enough that it would have been noticeable only to instruments, not to the people on board. The energy is there, the destruction is not yet. As the waves enter shallower water, everything changes. The physics of wave propagation in shallow water are fundamentally different from wave propagation in deep water. As the water depth decreases, the speed of the wave decreases, but the energy of the wave is conserved. Since the wave is moving more slowly, and the same amount of energy is being carried through a smaller cross-section of water, the wave has to go somewhere. It goes up. The relationship between water depth and wave height follows a physical law, and the numbers that the law produces for the Storegga tsunami are extraordinary. Modelling studies suggest that as the wave train entered the shallow waters of the northern North Sea and began to interact with the shelf and the coastline of what is now Scotland, individual wave heights may have reached 20 metres or more in certain locations. At the Shetland Islands, which lay directly in the path of the approaching wave train, sediment deposits found by geologists in the 1980s and confirmed by subsequent research show evidence of tsunami inundation reaching heights of around 20 metres above the contemporary sea level. At the Scottish mainland coast, the evidence suggests waves of perhaps 10 to 15 metres in the most exposed locations. Dr. Ingrid has modelled the Storegga tsunami many times, using different assumptions about the geometry of the slide, the water depth at the time of the event, and the bathymetry of the ancient North Sea. Each model produces slightly different numbers, and she is careful to present the range of possibilities rather than a single definitive figure. What all her models agree on is the order of magnitude. This was not a wave that would have swept a few meters up a beach and then retreated. This was a wave that would have penetrated kilometers inland in the low-lying coastal areas of what is now eastern Scotland. It was a wave that would have reached the Doggerbank and the low-lying plains of Doggerland. It was a wave that would have been visible from far out at sea as a darkness on the horizon, a line of confused and churning water moving at impossible speed toward the shore. The warning time for people on the coast of what is now northeastern Scotland would have been somewhere between 2 and 4 hours from the time the slide occurred. This sounds like a significant warning window, but it is only a warning window if you know what the signs mean. A large earthquake offshore, a strange withdrawal of the sea from the beach as the trough preceding the first wave crest pulls water away from the shore. An unusual sound, a distant roar growing louder. These are the classical precursors of a tsunami, and they are recognized today by communities in tsunami-prone regions of the world. 8,200 years ago, in a world without any prior experience of this specific phenomenon, or at least without any living memory of it, they would have been profoundly mysterious, unprecedented, and terrible. What happened in the minutes before the wave arrived would have been visible in the sea itself. The withdrawal of the water from beaches and shallow coastal areas, the trough of the wave arriving before the crest, would have exposed sea floor that had never been seen before, stranded fish, left boats sitting on bare mud where minutes before there had been a meter of water. Some people would have gone toward this strange sight out of curiosity. Some would have run from it, responding to an instinct that they could not have articulated, but that the body sometimes knows before the mind catches up. In the accounts of modern tsunamis, both responses are documented. Both were probably present on the shores of ancient Doggerland and northern Scotland on the morning of the Storegga event. The wave reached the Shetland Islands first, or what would become the Shetland Islands. In the sea level conditions of 8,200 years ago, the landmass that is now the Shetland archipelago was still largely connected. A single island rather than a scattered group, sitting in the direct path of the approaching wave train. The sediment record there is among the most compelling evidence for the event that exists anywhere in the world. In the 1980s, geologists working in the Shetlands found a layer of sand in coastal peat deposits that had no obvious explanation in the normal range of storm and flood events. Sand layers in peat are not unusual. Storms can deposit sand on coastal margins, and this sand can be preserved in the organic sediment that accumulates in boggy ground. But this sand layer was different. It was too thick, too laterally extensive, too uniform in its characteristics to have been deposited by any storm that the Shetland climate could plausibly produce. And it contained within it evidence of the ocean, marine microfossils, fragments of shell, material from the seafloor, transported far inland and deposited at elevations well above the normal reach of storm waves. When the age of this sand layer was determined, it matched the timing of the Storegga slide exactly. The sand layer was the Storegga tsunami, preserved in the peat of the Shetland coastline, sitting undisturbed for 8,000 years until a geologist's trowel found it. Since that initial discovery, similar sand layers of the same age have been found at sites along the eastern coast of Scotland, at sites in Norway, at sites in the Faroes and Iceland. Each one tells the same story from a slightly different angle. The wave reaching a particular coastline, depositing its cargo of marine sediment at a particular height, retreating and leaving behind a geological signature that is unambiguous once you know what to look for. Together, these deposits allow scientists to map the reach of the tsunami across the entire region and to estimate with reasonable confidence the heights that the waves achieved at different points along the coast. Rowan has excavated several of these tsunami sand layers in her career, and she describes the experience in terms that go beyond the professional. The sand layer itself is not dramatic to look at. It is a pale yellowish band, a few centimeters to perhaps 30 centimeters thick depending on the location, sitting between layers of dark organic peat. But when you know what it is, when you understand that you're looking at the physical record of a single morning 8,000 years ago, when you understand that the marine microfossils in this sand were living on the seafloor hours before they were deposited here, far inland on what was then dry land, it becomes something else. It becomes a document. The oldest document of human catastrophe in the British Isles. The question of how many people were in the impact zone when the wave arrived is one that cannot be answered with certainty, but it can be approached through the population estimates that archaeologists have developed for Mesolithic Britain and Doggerland. The total human population of the British Isles and the adjacent areas of continental Europe in this period was probably in the range of several thousand to perhaps 10,000 individuals, small by any modern standard, but significant relative to the carrying capacity of the landscape and the density of known archaeological sites. The coastal areas and the wetlands of Doggerland were almost certainly among the most densely populated parts of this world. The coastal zone in a hunter-gatherer economy is one of the richest and most productive environments available, offering simultaneously the resources of the land and the sea and the transition zone between them. The people of Doggerland would have been concentrated along the coasts and river systems, precisely the areas most exposed to the tsunami. The higher ground of the Dogger Bank might have offered some safety to those who were on it when the wave arrived. The low-lying coastal margins, the beaches and river mouths and tidal flats, offered none. Calder is on higher ground when the wave comes, not because he anticipated it, not because he read the signs correctly and ran for safety, but because the particular rhythm of his life on that particular morning has placed him there. He has been moving to a new camp, following game, or returning from a successful hunt on the higher plateau. The specific reason does not matter. What matters is that the wave crests break below him, that the churning white water reaches a line on the slope below his position and stops, and that when the sea retreats, it leaves behind a transformed world. The camps of people he knows are gone. The familiar landmarks of the lower ground are submerged. The low-lying paths between the Dogger Bank and the eastern shore of what would become Britain are under water in a way that is new, that has never been seen before, that will not drain away like a spring flood. This water is staying. The Storegga tsunami did not drown Doggerland on its own. This is one of the most important nuances in the story, and one that is sometimes lost in the more dramatic tellings. The tsunami was catastrophic and sudden, and it killed people and destroyed communities and permanently altered the landscape in specific ways. But the submersion of Doggerland, the long process by which a land the size of France disappeared beneath the North Sea, was the work of thousands of years, not a single morning. What the tsunami did was accelerate and intensify a process that was already underway, and potentially deliver a fatal blow to communities that were already living on the margins of a shrinking world. Sea levels had been rising for more than 10,000 years by the time the Storegga event occurred. The low-lying western and southern parts of Doggerland had already been swallowed. The higher central areas were still above water, but they were being squeezed, the coastlines advancing on all sides, the land area available to human communities diminishing with each decade. The tsunami, arriving at this moment of already stressed geography, would have done several things. First, it would have stripped the vegetation and soil from the coastal margins of what remained of Doggerland, leaving bare sediment exposed to the accelerating erosion of the sea. Second, it would have broken through or overtopped the natural barriers, the sandbars and beaches and low ridges that were holding the encroaching sea at bay in specific locations, allowing salt water to penetrate into areas that had previously been freshwater wetland. Third, the sheer mechanical energy of the wave and its backwash would have rearranged the underwater topography in ways that changed the currents and the sediment dynamics of the region for centuries afterward. Rowan thinks about this process in terms of resilience. The landscape of Doggerland before the tsunami had a kind of resilience. It was changing, but it was changing at a pace that human communities could adapt to. Families moved. Knowledge was updated. The territory contracted, but the communities persisted within it, adjusting their ranges and their relationships to the landscape as the landscape changed. The tsunami broke that resilience. Not because it was necessarily more destructive than a prolonged period of sea level rise would eventually have been anyway. The the total volume of land lost was not dramatically different, but because it happened so fast that adaptation was impossible. The knowledge of the landscape that a community had built up over generations was suddenly irrelevant, because the landscape it described no longer existed. The specific fate of the Dogger Bank, the high ground that persisted longest above water, is a matter of ongoing scientific investigation. The most current evidence suggests that it remained above water for some time after the main Storegga event, but that the changed dynamics of the North Sea following the tsunami accelerated its eventual submersion. Whether it persisted as a low island for centuries or disappeared relatively quickly in the aftermath of the wave is not yet known with certainty. What is known is that by approximately 7,000 years ago, roughly 1,200 years after the Storegga event, the last remnants of Doggerland had been claimed by the sea. The island of Britain, separated from continental Europe, was essentially the shape it is today. The human communities that survived the tsunami in the areas around Doggerland, on the higher ground of what is now eastern Scotland, on the remnant lands of the bank itself, on the edges of what is now the European mainland, faced a landscape that was fundamentally altered. The familiar routes of movement, the known crossing points between the higher ground and the river valleys, the camps that had been used for generations, all of these were either gone or transformed. The social networks that connected communities across the landscape of Doggerland, the exchange of people and materials and knowledge that the archaeology hints at through the distribution of particular flint types and tool forms across the region, were disrupted or destroyed. The Mesolithic people who lived through the Storegga tsunami and its aftermath are, in a profound sense, invisible to us. They left no written accounts. They built no monuments that have survived. Their traces in the archaeological record are thin and fragmentary. The occasional flint scatter, a hearth of burned stones, a midden of shellfish and animal bone. The residue of lives lived lightly on the landscape, in the manner of highly mobile hunter-gatherers who carry most of what they need with them and leave little behind. But the silence of the direct record does not mean that nothing can be known. The archaeology of the post-tsunami period in Britain and the adjacent continental areas shows patterns of change that are consistent with the kind of disruption and reorganization that a catastrophic event would produce. Population movements, changes in the distribution of particular tool types and raw materials, the appearance of new technologies and the disappearance of old ones. None of these changes can be attributed with certainty to the Storegga event. The archaeological record is too fragmentary, and the dating too imprecise for that level of specificity. But the patterns are there, and they are consistent with what you would expect from a community that has lost a significant portion of its homeland and been forced to reorganize itself in response. Calder's experience in the aftermath of the wave is the experience of loss compounded by disorientation. The landscape he carries in his memory, the mental map that a skilled hunter-gatherer builds up over a lifetime of moving through a particular territory, no longer matches the landscape in front of him. The paths he knows lead to places that are now underwater. The camps he knows are gone. The people he knows who were in the lower areas when the wave came are gone. He's alive, on high ground, with whatever he was carrying when the morning turned catastrophic, and the world he knew is beneath the sea. What does a community do after a catastrophe of this magnitude? The anthropological literature on disaster response in small-scale societies suggests several possibilities. Some communities break apart under the strain, the survivors dispersing into the territories of neighboring groups, their identity as a distinct community ending. Others cohere more tightly around the shared experience of loss and survival, the trauma becoming the defining event of a collective identity that is transmitted to subsequent generations in stories and rituals. Others do both simultaneously, some individuals and family groups dispersing while others remain together, the community fragmenting and reconstituting itself in a new form around a smaller core. The evidence from the Mesolithic archaeology of Britain in the centuries after the Storegga event is ambiguous enough to be consistent with all of these responses. What is clear is that the Mesolithic people of Britain and the adjacent areas of continental Europe did survive. The genetic record, readable now from ancient DNA extracted from skeletal remains, shows continuity of population through this period. The people did not disappear. They adapted. They always adapted. The Mesolithic record of Britain and Europe is, in the deepest sense, a record of adaptability, of communities that have been managing climate change and sea level rise, and the transformation of their landscape for thousands of years before the Storegga event, and that continue to manage it for thousands of years afterward. Rowan has excavated sites in the coastal peat deposits of the North Sea margins that date to the period immediately after the Storegga tsunami, and she finds in them a particular quality of attention that she struggles to put into words without sounding unscientific. The people who used these sites were paying very close attention to the sea. The evidence, the density of marine food remains, the positioning of the sites relative to the contemporaneous shoreline, the evidence of repeated use over many years, suggests communities that were intensely focused on the water, monitoring it, using it, living at its edge with a care and an awareness that may be the behavioral residue of the catastrophe that had so recently reshaped their world. The claim that the Storegga tsunami created Britain is one of those historical assertions that is both true and not true simultaneously, in the specific way that powerful simplifications always contain both a real insight and a real distortion. The insight is this: the Storegga tsunami was a genuine turning point in the physical geography of northwestern Europe, an event that accelerated the final separation of Britain from continental Europe, and that left the North Sea in something much closer to its modern configuration. The distortion is this: Britain's separation from Europe was not the work of a single wave on a single morning, but a process that took thousands of years, and that the tsunami interrupted and accelerated rather than created from scratch. The specific question of whether Britain was still physically connected to continental Europe at the time of the Storegga event is one that scientists have debated, and the answer depends partly on what you mean by connected. The land bridge between what is now southern England and what is now northern France, the chalk ridge that connected the two, had probably already been breached by the time of the Storegga event, creating the English Channel as a marine waterway, though the precise timing of this breaching is itself a matter of ongoing investigation. If the channel had already opened, then Britain was already technically an island, though an island very close to the continent, separated by shallow water that could perhaps be crossed in favourable conditions. What the Storegga tsunami did was to deal a decisive blow to the remaining land connections and near connections that still allowed meaningful movement between Britain and the continent across the southern North Sea, by flooding the low-lying areas of Doggerland, by accelerating the erosion of the coastal margins, by permanently altering the underwater topography and the dynamics of the tidal and current systems of the southern North Sea. It made the crossing from Britain to continental Europe something qualitatively different from what it had been before. Not impossible. People were making sea crossings in this period, as the archaeological evidence clearly demonstrates, but significantly more difficult, more dependent on technology, more hazardous, more weather-dependent. The casual interchange of people and animals and materials across a landscape of wetland and river, an occasional low-water crossing, became the deliberate, dangerous, technology-dependent voyage across a significant body of open water. Dr. Ingrid is careful about the claim that her subject of study created Britain. She finds it both compelling as a narrative and professionally uncomfortable as a scientific assertion. The tsunami is real. The evidence for it is solid. The broad outlines of its effects on the landscape are well understood. What is less certain is the specific timing of Britain's final physical separation, and whether the tsunami was the decisive event or merely one of several that contributed to an outcome that was geologically inevitable, given the sea level trends of the period. She prefers to say that the tsunami was one of the key moments in a longer story, and that it may have been the moment that made the separation feel final to the people who experienced it, even if the geological process that the tsunami embodied had been running for thousands of years. The question of what Britain's island status meant for the people who lived there, and for the subsequent development of the cultures that would eventually become the civilizations of northwestern Europe, is one that goes far beyond the scope of a geological event. The separation of Britain from the continent did not prevent continued movement of people and materials across the Channel and the North Sea. The Neolithic agricultural revolution reached Britain eventually, brought by people who crossed the sea with their animals and their seed grain and their cultural practices. The Bronze Age metalworking traditions, the Iron Age hill fort cultures, the Roman invasion, the Anglo-Saxon migrations. All of these involved the crossing of the waters that the Storegga tsunami helped to consolidate. Britain's island status shaped its history profoundly, but it did not isolate it. It made its connections to the wider world deliberate rather than casual, consequential rather than incidental, which may be a more interesting outcome than simple isolation. The scientific reconstruction of the Storegga tsunami is a story of remarkable ingenuity and patience, of researchers finding ways to read the evidence of an 8,000-year-old event from the most unlikely sources. The work has taken place across multiple disciplines and multiple countries over several decades, and it continues today as new techniques and new data sources become available. The tsunami sand layers that have been found along the coasts of Scotland, Norway, and the Shetland and Faroe Islands are the most direct evidence, but their interpretation requires careful work. A sand layer in a peat deposit is not automatically a tsunami deposit. It could be the product of a particularly severe storm, of a period of increased erosion from an upstream source, of a temporary change in local hydrological conditions. The process of ruling out these alternative explanations and confirming a tsunami origin requires a combination of sedimentological analysis, examining the grain size, sorting and composition of the sand, and microfossil analysis, identifying the marine organisms whose remains are mixed into the deposit, and radiocarbon dating, establishing the age of organic material immediately above and below the sand layer. Rowan describes the radiocarbon dating process as the moment of truth in tsunami layer research. You have a sand layer that looks like it might be a tsunami deposit, that contains the right kinds of marine microfossils, that has the right sedimentological characteristics. But until you have the age, you cannot be sure. The age is what connects the physical evidence to the historical event. When the dates come back and they cluster around 8,200 years before present, when they match the age of the Storegga slide as determined from the deep-sea sediment cores off the Norwegian coast, that is the moment when the sand layer stops being an interesting geological anomaly and becomes a piece of history. The sediment cores from the Storegga slide itself provide a complementary line of evidence. The slide is preserved on the seafloor as an enormous topographic scar. The missing material is visible as a depression, the deposited material visible as a thick accumulation on the abyssal plain at the foot of the continental slope. Cores taken from the edge of this slide, deposit and from undisturbed sediment nearby, allow scientists to date the event with reasonable precision and to characterize the nature of the sediment that failed. The cores show the layers of sediment that were deposited before the slide, the abrupt gap where the slide material was removed, and the sediment that has accumulated since. The age of organic material at the base of the post-slide sediment gives a minimum age for the event. The age of organic material at the top of the pre-slide sediment gives a maximum age. The two brackets converge on approximately 8,200 years ago. Submerged forest and peat deposits found along the coastlines of Britain and Ireland provide another window into the world before the final submersion of Doggerland. At low tide in many locations around the British coastline, particularly in sheltered estuaries and along the exposed rock platforms of western and northern shores, ancient tree stumps and peat layers are visible at or just below the present high water mark. These are the remnants of forest that grew on land that is now below the sea, preserved in waterlogged conditions that have prevented their decay. The trees are rooted where they grew. They were not transported there by any flood, which means that the sea level at the time they grew was lower than the present sea level, by at least the height of their root zones above the current sea floor. Rowan has worked at several of these submerged forest sites, and she finds them among the most evocative physical connections to the lost world of Doggerland. Standing in a tidal channel at low water, looking at the roots of an oak tree that grew 8,000 years ago in what was then a coastal woodland, is a direct physical encounter with the fact of sea level change in a way that a graph or a sediment core simply cannot provide. The tree is real. It grew here in a real landscape, tended by real weather and real seasons. And now it is at the edge of the sea, exposed only at low tide, the last visible remnant of a world that the sea has taken. The question of whether the Storegga tsunami left traces in the cultural memory of the people who experienced it, whether the story of the wave and the drowning of Doggerland echoes in any of the myths and legends that have come down to us from the ancient Celtic and Germanic and Norse traditions of northwestern Europe, is one of the most fascinating and most contested questions in the entire Storegga research program. It is a question that requires very careful handling. The temptation to connect ancient myths to ancient geological events is powerful and has a long history in scholarship, from the identification of the biblical flood with various Mesopotamian geological events, to the suggestion that Plato's Atlantis preserves a memory of some real sunken civilization. Most of these connections, when examined carefully, turn out to be either too vague to be meaningful. Any myth involving water can be connected to any flood event if the criteria for connection are loose enough, or too chronologically distant to be plausible as oral transmission. The specific case for Storegga is somewhat more interesting than most, because the event is relatively recent in geological terms, because it affected a specific and well-defined region from which the relevant oral traditions come, and because the time depth involved, 8,200 years, is not absurdly beyond the demonstrated capabilities of oral tradition. Research on the oral traditions of Aboriginal Australians has suggested that some stories about sea level change and the flooding of coastal areas may preserve genuine memories of events that occurred more than 10,000 years ago, calibrated against the independently established geological record of sea level rise in those regions. In the Norse and Celtic traditions of northwestern Europe, there are flood myths and stories of sunken lands that have attracted scholarly attention in this context. The Welsh legend of the drowned kingdom of Cantre'r Gwaelod, lying under the waters of Cardigan Bay, with its church bells audible under the sea in certain conditions, is one example. The Norse accounts of the gradual drowning of coastal lands, preserved in the sagas as stories of the sea claiming farmland and villages over generations, are another. The Irish traditions of drowned cities and sunken forests, still echoing in the folk memory of coastal communities, are a third. None of these stories can be directly connected to the Storegga tsunami with confidence. They're too geographically dispersed, too chronologically vague, too overlaid with mythological and narrative conventions to serve as reliable historical documents. But they are also not nothing. They are evidence of a cultural tradition that took the loss of coastal land to the sea seriously enough to preserve the memory of it across many generations, in stories that were told around fires and passed from parents to children, and that survived long enough to be written down eventually. The sea that takes the land is a recurring presence in the imagination of the people who have lived on its margins, and the reason it recurs is that it is real. The sea does take the land. It took Doggerland. It took Cantre'r Gwaelod, or something that the legend of Cantre'r Gwaelod is remembering. It takes, in smaller increments, coastline all around the British Isles every year. Dr. Ingrid is sceptical of the direct connection between specific myths and the Storegga tsunami, but she is not dismissive of the broader cultural resonance of the event. What she finds compelling is not the question of whether any specific legend preserves a specific memory of a specific wave, but the question of how communities process and transmit the experience of catastrophic landscape change. The Storegga tsunami was the largest geological event to affect northwestern Europe in the entire period of human habitation. It killed people and destroyed communities and permanently altered a landscape that tens of thousands of people called home. It would be more surprising if it left no cultural trace at all than if it left traces that are now unrecognizable under thousands of years of retelling and transformation. Called a story, the composite experience of surviving the tsunami and living in its aftermath becomes, in this framing, the origin of a story. Not a specific story that we can identify in the surviving tradition, but a story of the type that the tradition preserves. The world that was before the flood, the catastrophe that ended it, the survivors who carried the memory forward into a changed world. This is the structure of flood myths everywhere. And if the Storegga tsunami was a real contribution to the deep cultural memory of northwestern Europe, this is how it would appear. Not as a specific identifiable account of a specific wave, but as one of the geological realities that gave the flood myth its emotional truth and its cultural staying power. The Storegga tsunami is not only ancient history, it is a demonstration of a type of event that is still possible, that the submarine landslide that produced it was not unique in geological terms, that other potentially unstable slopes exist on the continental margins of the North Atlantic and elsewhere, and that the monitoring and understanding of these slopes is a genuine component of modern coastal risk management. The Norwegian coast has been the focus of intensive scientific monitoring for this reason. The Norwegian Meteorological Institute and the Norwegian Geological Survey maintain programs of seafloor observation and sediment analysis specifically aimed at identifying potentially unstable areas on the continental shelf and assessing the probability and potential magnitude of future events. This is not panic or alarmism. It is the rational response of a scientific community that has understood, through the study of events like Storegga, that the seafloor is not static and that the consequences of its movement can be profound. Dr. Ingrid is involved in this monitoring work, and she describes it as the part of her research that feels most directly connected to the present. The Storegga event is history. The physics that produced it are not. The sediment that has accumulated on the Norwegian shelf since the Storegga slide represents 8,000 years of new deposition, not yet at the volume or the configuration that made the Storegga area unstable, but a reminder that geological time is longer than human time, and that processes that operate on geological timescales can produce events that happen on human timescales. The relationship between climate change and submarine landslide risk is one of the more unsettling intersections of earth science and contemporary concern. As ocean temperatures rise, the stability of methane hydrate deposits on continental shelves, ice-like compounds in which methane gas is locked into a solid form by the combination of low temperature and high pressure, may be affected. The destabilization of these hydrate deposits, releasing the gas they contain, has been proposed as a contributing factor to the original Storegga instability, and the possibility that warming ocean temperatures could trigger similar processes in the present or near future is a live area of research. The science here is genuinely uncertain. The mechanisms are complex, the timescales are unclear, and the risk is not easily quantified. But the question is being asked, which is the appropriate response to a genuine uncertainty with potentially serious consequences. Beyond the specific question of submarine landslide risk, the Storegga tsunami teaches a broader lesson about the relationship between slow change and sudden events. The tsunami was dramatic and catastrophic, and it happened in a matter of hours, but it was embedded in a much longer process, the gradual sea level rise of the post-glacial period, that had been transforming the landscapes of northwestern Europe for more than 10,000 years before the wave. The tsunami did not create the conditions that made Doggerland vulnerable. Those conditions had been created slowly over millennia by the rise of the sea. The tsunami was the crisis that a long period of slow change had been building toward. This pattern, slow change creating vulnerability, sudden event producing crisis, is one that appears repeatedly in both natural and human systems. The gradual rise of CO2 in the atmosphere creating conditions of increasing risk, the sudden weather event that produces a flood or a heat wave, the gradual erosion of a social or political institution over decades, the single crisis that brings it down, the slowly rising water table that makes a slope increasingly unstable, the earthquake or the rainfall event that finally triggers the landslide. Understanding the relationship between the slow and the sudden, between the background process and the triggering event, is one of the central challenges of risk assessment in every domain, from geology to economics to public health. Rowan thinks about this in terms of her own work on the North Sea coastlines. The coasts she studies are changing, and the change is accelerating. The same processes that drowned Doggerland, sea level rise, storm erosion, the undermining of coastal defences, are active today, operating on a coastline that is now densely populated and economically critical in ways that Mesolithic Doggerland was not. The lessons of Storegga are not comfortable ones for a modern coastal engineer or a planning authority responsible for a low-lying estuary town. They are lessons about the limits of human control over the sea, about the capacity of the sea to act suddenly and without warning after a long period of apparently manageable incremental change. The sea's work is slow and it is sudden. It is the patient accumulation of millimeters of water across centuries, and it is the wave that comes in the night and remakes the world between sunset and sunrise. The story of Doggerland and the Storegga tsunami is both of these things simultaneously. It is the 10,000-year story of a landscape slowly claimed by the rising sea, and it is the single morning on which that slow story was interrupted by something fast and violent and final. What we know about that morning is remarkable, given how long ago it was and how completely the world it described has been submerged. We know from the sediment cores and the tsunami sand layers and the underwater topographic surveys that a wave of enormous power struck the coasts of what is now Scotland and Norway and the islands of the northern seas on a specific morning approximately 8,200 years ago. We know that this wave was generated by a submarine landslide of extraordinary scale off the Norwegian coast. We know that it reached heights of tens of meters in the most exposed coastal locations, that it penetrated kilometers inland in the low-lying areas, that it deposited a characteristic layer of marine sediment that can be identified and dated in the geological record across the entire region. What we do not know, what we may never know with certainty, is the full human story of that morning. How many people were in the impact zone? How many survived? What happened in the communities that were disrupted? What was lost, not just geographically and ecologically, but culturally and socially? The stories, the knowledge, the relationships, the ways of understanding the world that existed only in the minds of the people who did not survive. These are absences in the record that cannot be filled by any amount of sediment analysis or seismic survey, because they were never written down and they did not leave a physical trace. What remains is what the sea left behind: the sand layers and the peat deposits and the submerged tree stumps and the scattered artifacts on the sea floor. And what the people left behind: the flint tools and the worked bone and the occasional piece of wood shaped by human hands, preserved by the anaerobic conditions of the submarine environment in ways that no one who made them could possibly have anticipated. These objects are not the full story, but they are a story, and Rowan and Dr. Ingrid and the many other researchers who work on this period are still reading it, still finding new chapters in the sediment and the seismic data, still being surprised by what the drowned world has to tell. Calder's story ends where it began, in motion, in adaptation, in the particular form of resilience that has characterized the human relationship with this landscape for thousands of years before the wave and thousands of years after it. He does not know that he is living through a turning point in the history of a world that will eventually call itself Britain. He does not know that the landscape he is moving through will be reconstructed from seismic data by scientists 8,000 years in his future. He knows the weight of his pack and the direction of the wind and the approximate distance to the next reliable water source. He knows that the people he is with are alive and that the people who are below him when the wave came are not. He knows that the world has changed and that he must change with it. He has always known this. It has always been true. It will go on being true long after the sea has finished its work. The sea is still working. It is working on the coasts of Britain tonight, as it has worked on them every night for 8,000 years since the Storegga wave reshaped them. The process is slower now than it was then, in one sense. There is no wave coming. In another sense, it is faster, because the rate of sea level rise driven by the warming of the planet is accelerating in ways that have no precedent in the 8,000-year history of the post-Storegga coastline. The lesson of Doggerland is not that catastrophe is inevitable. It is that the sea is patient and the sea is powerful, and that the landscapes we inherit are not permanent, and that the people who have understood this best have always been the ones who watch the water most carefully. This has been Midnight Chronicle. Sleep well, wherever in the world you are tonight.